Hi everyone, we'll start out today's video with another little comic here. A lot of the things that I pull from xkcd.com. It's a website made by actually a physicist, Randall Munroe. He's written some books and occasionally has some pretty funny content out there. You might find it silly, that's okay. It's kind of a way for me to get my personality across a little bit, the things I find entertaining even though we're in this online environment. Anyway, on with the lesson. Today we're going to cover section 1.3 titled Vector Equations. And we're going to first discuss vectors in R2. Okay, R2 is our two-dimensional space, and the way that you can write that down, it's a capital R that you make like that, and a superscript 2. Let me do it one more time for you. I don't make them the most beautiful, but that's kind of what I'm looking for right there when you write them yourself, and you will as we move through the semester. Okay, so vectors in R2, a matrix with only one column matrix is called a column vector or just a vector. But one column in a matrix makes a column vector. An example of a vector with two entries looks like that. W has two entries, W1, W2, one column, it's a column vector. The W's are real numbers. And we say the set of all vectors with two entries is denoted by R2. So that capital R, it stands for the real numbers that appear as entries in the vector, and the exponent 2 tells me that there are two entries. So if I have a capital R and a 3, there's going to be 3 entries. Two vectors in R2 are equal if and only if their corresponding entries are equal. If I have two vectors u and v, their sum is the vector u plus v, and that is obtained by adding their corresponding entries. If you've taken some upper level courses in the past, you may have already dealt with vectors quite extensively. We're going to see them throughout this course and always write them as column vectors. If I have a vector u and a scalar c, a real number c, it's called a scalar. A scalar multiple of u, by c is the vector c times u, obtained by multiplying each entry in u by that c. Okay, that's called a scalar multiple of u. We'll look at a quick example here where I have a vector u with those entries, and and a vector v with those entries. And first I want to find 4u. Okay, so I find 4 times the vector u by multiplying 4 times that column vector, and we're going to multiply it by each individual entry in the vector. All right, and then negative 3 times v, we're going to multiply negative 3 times each entry in the v vector, and that's going to give me negative 6, positive 15, and then we're going to find that sum there, 4 times u plus negative 3 times v, and, well, we've already got 4 times u, that's 4 minus 8, and we're going to add to that our negative 3v minus 6, 15. Oops, do that a little better there. And when you take that sum, add the corresponding entries together, you get negative 2 and positive 7. So there's a little vector operations. So now we talk about a geometric description of R2. What does it look like visually? Right, our rectangular coordinate system that you've seen for years in math classes. Consider that in a plane, because each point in the plane is determined by an ordered pair of numbers. We can identify the point parentheses a comma b with the column vector ab. So taking that and connecting those two pieces together, our R2 that we're referring to in this section is the set of all points in the plane, in the xy plane. However, in our text, they refer to it as the x1, x2 plane. So I'll draw a quick example here. All right, so here's my x1 axis, my x2 axis. I mean, clearly you can think of them as x's and y's. There's nothing wrong with that. But if I have my vector here in space, trying to draw a straight line there, not very well. There's my vector, and I'm going to label that point as negative 3 comma, or no, it wouldn't be negative 3, it'd be 3, comma, negative 1, right? I can write that vector as 3, negative 1 as a column vector. So now that we're connected in this to a rectangular coordinate system, what does our addition look like? What does the vector u plus v look like in the xy plane, the x1, x2 plane? Right? If I have u and v in R2, they're points in the plane. Their sum corresponds to the fourth vertex of the parallelogram, whose other vertices are u, 0, and v, the 0 being the 0 vector. So my vector u plus v is up here at that point. And if you've taken like physics in the past, you would certainly have learned the tip to tail rule. So this is also my vector u from over on the left. Okay, and that's what the vector addition looks like. If I have the vectors listed, I can just add the corresponding entries, or visually, geometrically, I use that tip to tail rule and have this parallelogram looking picture here. Okay, on our next slide, vectors in R3, we have 3x1 column matrices. They would be points in a three-dimensional space, right? X, Y, Z plane, or X1, X2, X3, or not plane, but space. All right, and then if I have any positive integer, Rn, excuse me, Rn, that is a collection of all lists of ordered, the word here is n-tuples. It's like double, triple, quintuple, quadruple. This is the n-tuple of n real numbers, written as an n by 1 column matrix like this. So with the dot, dot, dot there, that stands for u1, u2, u3, u4, u5, u6, all the way up to the last vector un. So there's n vectors in that, or n entries in that column matrix. This next slide lists the properties of Rn. I'm not going to read every single one of them for you, but you should look through them. They should be familiar, right? They're all things that you've seen before, but these apply to any vector matrix, any column vector in Rn, right? The first one, that sure looks like the commutative property. We've got the associative property, identity property. These are all things you've seen before, and this slide, this page in your textbook, is just saying all of those properties that you're familiar with, they apply to this concept also. Because as you get into upper level maths, you'll find that sometimes we enter into some system where not all of the properties apply. And that'll happen in this course also. We'll get to a point where not every familiar property applies to the space that we're in. Now we get to one of the key definitions in this section, and that is a linear combination. Okay, so if I have a set of vectors, so that's v1, v2, v3, v4, v5 through vp, so p vectors in Rn, and I have scalars C1 through CP, C1, C2, 3, 4, 5, so P vectors and P scalars. The vector Y is defined by Y equals C1 V1 plus C2 V2, et cetera, up to CP VP. It is called a linear combination of V1 through VP with weights C1 through CP. Okay, so what I'm basically saying here is that my vector, I can form a vector y using given vectors and given scalars. It's a linear combination of those vectors and scalars. Then the bottom bullet point here, the weights in a linear combination can be any real numbers, including 0. I might not need v2 to form the vector y. I might not need v4 to form the vector y. So those might have a coefficient of 0 in front of them. Now, I apologize in advance for how terrible this picture looks. I would normally go to the document camera and show the book or pull up the ebook, but this is the best way that I could throw this picture in the notes and then talk about it. We're looking at an example here, and I have a vector v1 and a vector v2. Okay, so let's first find out where they are. Right, v1 is right here, negative 1, 1. Left 1, up 1. That's vector v1. v2, 2, 1. Over 1, 2, up 1. If you notice, the rectangular grid is not on this picture, right? We've got the dotted lines here to show the x and y axes, but I'm not given that rectangular grid. I have a grid that's made up of v1s and v2s. And so that's what this is showing here. This is 1v1, 2v1, 3v1. This is 1v2, 2v2, 3v2. And what we can do is show how to make vectors u and v. So let me point out where they are. How can I get vector u and vector w, excuse me, how can I build them out of v1 and v2? So how can I get u as a linear combination of the v vectors? Okay, and the way that we do that, it's kind of cool. So stick with me here for a minute. Right, if I go v1, v1, and v1, that's 3v1. So 3 units in the v1 direction. And then there's the v2 direction, but I'm going backwards. So that's a negative v2, and that's another negative v2. Notice how now I got to my u vector, right? So how did I get to u? I built u by going, and let me write this at the bottom here, u is equal to 3v1 minus 2v2. That's how I got there. That's how I built that vector out of v1 and v2. So u is a linear combination of the v vectors. Okay, and how do I get to w, right? Well, let's see. I definitely need to, let me change colors here. Let's go with green. I definitely need 1v1. I definitely need 2v1, but then I'm only going to go like another half-ish. And then I need to go backwards half-ish of a v2. And so what my w vector, w, is equal to, let's say, 2.5 v1 minus a half. I don't know why I wrote 0.5 and then 1/2. Minus a half v2. And so now I've got w as a linear combination of u and v. And right, you can look at some other examples in this one, but those are the two that we needed to figure out for this example. Okay, so that's how we can geometrically establish linear combinations, and we'll see what happens with the next example, how we do that algebraically. Okay, in our example here, we're given an a vector, a1 and a2, so 2 different a vectors, and then a b vector. Okay, it says determine whether b can be generated as a linear combination of a1 and a2. Can I build the b vector using the a vectors? Can it be done? And then what that means is determine whether weights x1 and x2 exist. Do these two weights exist such that x1 times the a1 plus x2 times a2 generates my b vector? Okay, so that's what we are going to figure out in this example. And so what I want to do is I'm going to rewrite that equation there because that's going to be super helpful. x1a1 plus x2a2 equals b. Now I'm just going to substitute what I know to be, what I know I can substitute. a1 is 1, -2, -5, plus x2. a2 is 2 and 5 and 6, and b is 7, 4, -3. Okay, so there's our first step. Substitute our known values in. All right, well, let's rewrite this a little bit differently because we saw at the beginning of the section, I can multiply that scalar x1 into the first vector, x1 times 1, x1 times -2, and x1 times -5. So I scaled each entry in that vector. I'm going to do the same thing in the second vector, 2x2, 5x2, 6x2 equals 7, 4, and -3. Okay, this is looking a little bit better. It almost looks like a system of equations. Hint, hint, it is. How about I take these, whoops, not like that. How about I take these two vectors on the left and let's push them together. Let's find that sum as we did earlier in the section. x1 plus 2x2, -2x1 plus 5x2, -5x1 plus 6x2 equals 7, 4, -3. Hey, that's a system of equations, right? I could just as easily write that not using matrices. x1 plus 2x2 equals 7. -2x1 plus 5x2 equals 4. And -5x1 plus 6x2 equals -3. Awesome. Well, how do I solve that system of equations? Well, fortunately, you're in linear algebra and you just learned about row operations. So here's what we do. we're going to take that system, or even this system, I saw what I should do back there, and we're going to write an augmented matrix. 1, 2, and 7. I don't like where that 7 is. 1, 2, 7, -2, 5, 4, -5, 6, 3. There's my augmented matrix. Well, let's do some row operations. Notice I have my first pivot where I want it, so I'm going to write down 2 operations that are going to put zeros below that pivot. Double row 1, add row 2, store the result in row 2. 5 times row 1, add row 3, store the result in row 3. Row 1 stays the same. Row 2 becomes 0, 9, and 18. And row 3 becomes 0, 10 plus 6 is 16, and 5 times 7 is 35. And oh, look at that, I lost a negative in front of my 3. Luckily, I found it before it was too late. So that's a -3. So 5 times 7 is 35, minus 3 is 32. Okay, one step down. Let's keep going here. Take a look at rows 2 and 3. Step back from them for a minute. Notice I can scale row 2 by a 1/9 and leave it right in row 2. And I can divide row 3 by 16. Okay, so 1, 2, 7, 0, 1, 2, 0, 1, 2, identical rows. That's okay. Okay, so what are we going to do? We're going to negate row 2, add row 3, store the result in row 3. That's going to eliminate everything in this bottom row. If you get to the point, and and it's still early, you might not be there yet, you don't have to necessarily write down that row operation. I get why that's going to be a row of zeros. If you have 2 identical rows, the next step should show a row of zeros. Okay, so you don't always have to write out that work. But I also, in this step, want to use this 1 to eliminate the 2 above it, and then we can be done after this step. That'll be nice. Okay, so let's write down the row operation that's going to use a 1 to eliminate a 2. We're going to take -2 times row 2, add row 1, store the result in row 1. Okay, let's see what this next step looks like. Row 2 is 0, 1, 2, not changing. Row 3 is a row of zeros for the reasons I've already said. And then in this other operation, I'm taking -2 times 0 and adding 1. It stays a 1. Taking -2 times 1 and adding 2. Becomes a 0. -2 times 2 is -4. Add 7 is usually 3. Yes, 3. Okay, so that is reduced row echelon form. What does it mean? What did we solve for? Our variables were x1 and x2. x1 is 3. x2 is 2. So let me kind of zoom out and scroll back up to the top. What did we actually get here? Right, these are the weights. Let me highlight them. These are the weights in front of A1 and A2 for how we build vector B, right? So what we've established now is that B, whoops, not like that, that looks terrible. B is equal to 3 times A1 plus 2 times A2. And I will leave it to you to check that. But if you triple A1, double A2, add them together, see what you get. That is how I build B. Write B as a linear combination of A1 and A2. On our next slide, we get another definition here. This is another important one. Linear combination in the previous couple slides ago, and now we have a definition for span. They will use this word throughout the semester. If I have a set of vectors in Rn, then the set of all linear combinations, the set of all linear combinations of those vectors is denoted by the span of that set. So we write span, and then the squiggly brackets, the vectors, and then close the squiggly brackets. That is called the subset of Rn spanned by, or generated by the vectors v1 through vp. Okay, a little bit of an abstract definition. Once we have examples, hopefully it'll help to provide some clarity. So that is, the span of a set of vectors is the collection of all the vectors that can be written in this form with scalars c1 through cp. Okay, again, once we have examples, it will hopefully be clearer. Okay, but that's the definition for span. Okay, so now let's read through this next example and draw a picture. Let V be a non-zero vector in R3. Stop reading. I'm going to draw a picture. 3 dimensions. Let's see how well I can draw in 3 dimensions. Not too bad. I'm going to label this x1, x2, and x3. So I'm in 3 dimensions, and I'm going to draw a vector V. Starts at the origin and goes out to right there. Okay? Then the span of that one vector is the set of all scalar multiples of V, which is the set of points on the line in R3 through V and 0. Okay, so what does that mean? Think of a scalar multiple of V. What does that look like? Well, I have 2V or 3V or negative 1/2 V or pi times V. All those do is take my V vector and either make it longer or make it shorter or point it in the opposite direction. Okay, but the span of a single vector is a line in that space. It's a line in R3 in this case. That is what the span of a single vector looks like. In our last example, to close out the section, I'm not going to try and draw this picture. It's a little bit more complicated than I would accurately convey. Right now, what does the span of 2 vectors look like? I have vector u and vector v. They're in R3 again, so I'm in a 3-dimensional space, 2 vectors. And it also tells me v is not a multiple of u. That just means they don't lie on the same line. Then we're looking at the previous example. Okay. Now the span of those 2 vectors, the span of uv, is a plane in R3. Why is that? Right? Here's vector v. Here's vector u. The span of u gives me this line here, right? Just scalar multiples of u. The span of v gives me this line here, scalar multiples of v. But what about u plus v is right there? How about 2v plus u, 3v plus u? I can get all of these points all over the place, all over here, including beyond the picture, right? We could extend this. Oops, that was poorly drawn. We could extend this rectangular plane in all directions. So this is just, a small section of the plane that is generated by u and v. It would go in the negative direction. Okay, it would go in all directions, but a plane through 3-dimensional space is the span of those 2 vectors. And I'll close out the section with a question. If you are in R3, and what does the span of 3 vectors look like? 3 vectors that point all in different directions. Okay, think about that. If you want to answer me in an email, you can. It's just a good question to close out on. Thank you for listening. Let me know if you have questions on this content. Have a great day.